Good morning, class. We are looking at practice test number 2, covering inverse trigonometric functions, equations, and identities. We want to find the exact value, so we can look at tan of negative 2 pi over 3, which is the same as pi over 3. First, let's discuss the information, basic information about inverse functions. Y equals sine inverse x. X is sine y, where x is between -1 and y. Y is between negative pi over 2 and pi over 2. Remember, we had to do the restriction on the domain of every trigonometric function to make him a one-to-one function. Otherwise, none of them is. And so this was the restriction we put on sine, and now becomes the range for its inverse. And their composite function is x, as long as sine inverse sine x equals x, as long as x is between negative pi over 2 and pi over 2. And sine of sine inverse is x, as long as x for the sine inverse is between -1 and 1. And the rest of them follow. So let's quickly look at tangent. Again, the restriction on sine was between negative pi over 2 and pi over 2. The same thing goes for tangent, but the endpoints are not included. Cosine is between 0 and pi, because cosine is positive in the first quadrant, negative in the second quadrant. Cosecant is a 1 over sine, and it basically follows the sine. Secant is 1 over cosine and follows the cosine from 0 to pi. However, although cotangent is the reciprocal of tangent, that's not the way it works. It basically goes with cosine from 0 to pi. All right. So we want to find tan inverse of tan of negative 2 pi over 3. And tan of negative 2 pi over 3 is square root of 3. And tan inverse of square root of 3, it's pi over 3. Remember, negative 2 pi over 3, as we go in the negative direction, it puts us in the third quadrant. In the third quadrant, tangent is positive. And for the inverse, from negative pi over 2 to pi over 2, that gives us the first quadrant, which is pi over 3. Secant inverse of square root of 2, we set this equal to alpha, beta, gamma, x, however you choose that. By definition, secant alpha becomes square root of 2. Since we know secant is 1 over cosine, then we say cosine is the reciprocal of that 1 over square root of 2, which is the same as square root of 2 over 2. Therefore, cosine alpha equals square root of 2 over 2. Alpha becomes pi over 4. Cosine inverse of 1/2, again, let's set it equal to some variable such as theta. Therefore, by definition, cosine theta becomes 1/2, and therefore theta is pi over 3. Tan of cosine inverse of square root of 3 over 2. If we set this one to be some angle, some arc, such as beta, by definition, cosine Beta is square root of 3 over 2, and we are looking for tan of beta. So when cosine is square root of 3 over 2, then the angle, the arc, must be pi over 6. We want tan of beta, or tan of pi over 6, and we know it to be square root of 3 over 3. So that is the process in order not to make a mistake. Cosine of cosine inverse of 1.2. This is undefined. Why is that? Because this must be between negative 1 and 1. 1.2 is larger than 1. Remember, sine and cosine, their y-coordinate is between negative 1 and 1, and it can be the endpoints, namely negative 1 as well as positive. We want to find the exact value of cosine of sine inverse of negative 1/3, and we're going to look at it both ways just for the sake of the exam, so you'll be familiar with both. We can go with the unit circle. We can also go with identities. So if we let sine inverse of negative 1/3 be anything, alpha, beta, gamma, then you're looking for cosine of that. So let it be theta. By definition, we are looking for cosine theta. That's what we are looking for. So what does this mean? This means sine theta must be negative 1/3. And because sine is negative, and we are talking about the inverse, theta is between negative power 2 and power 2. It puts us in the fourth quadrant. And we are looking for cosine of that. And we know in the fourth quadrant, cosine is positive. So if we want to go with the unit circle, sine is negative 1 over 3, or y over r. So y becomes negative 1 and r is 3. Remember, r is always positive. And x becomes 2 square root of 2. Simply put, you can calculate it. When this is x, this is negative 1. When you square x and y, the same as squaring r. So x squared, that is missing, plus y squared, that is 1. X squared is 8, therefore x is 2 square root of 2, or square root of 8. And so cosine is x over r. It makes it 2 square root of 2 over 3. However, we can use the identities, and we remember Pythagorean identities. Sine squared plus cosine squared is 1. 1 plus tan squared is secant squared. 1 plus cotangent squared is cosecant squared. So if we use the first one, that gives us cosine is plus minus the square root of 1 minus sine squared, where sine is given as negative 1/3. And by the way, we always use plus minus, and then based on the quadrant, we figure out we want positive or negative. In quadrant 4, cosine is positive, therefore we're going to use the plus. By the way, again, I hope everybody can see that from here, we can come up with this, or we can come up with sine theta is plus minus the square root of 1 minus cosine squared. So we use the positive one. Negative 1/3 to the second power is 1 over 9. And 1 minus that is 8 over 9. So we're dealing with the square root of 8 over 9. And we know square root of 8 is 2 square root of 2, and 9 comes out as 3, and we are done. Right a trigonometric expression for sine of tan inverse of u as an algebraic expression, and we have several ways of approaching it. I'm going to go over a couple of them. For example, if we let tan inverse of u be theta, then tan theta by definition is u, and we are looking for sine theta. That's the idea behind that. We know that cotangent is 1 over u because it's the reciprocal of tangent. And that will help us get to sine, because 1 plus cotangent squared is cosecant squared, where cosecant is 1 over sine. So if we want to go with the identity, there are many identities involved here. So 1 plus cotangent squared is cosecant squared theta. And remember, sine is 1 over cosecant. So let's plug in. 1 plus 1 over u squared is cosecant squared theta. When we take a common denominator of u squared, this becomes u squared plus 1 over u squared. That's cosecant squared. And remember, cosecant and sine are reciprocals. Therefore, sine squared is the reciprocal of that. Sine squared is the reciprocal of that. So sine is plus minus the square root of that. And we take the u squared out as u. And sine and tangent have the same sign, because both of them go from negative power to power 2. In the case of a sine, the endpoints are also included. Another way of doing this, and sometimes it makes it faster and easier, is that if we go with a triangular format, tan is u, therefore u over 1, or opposite over adjacent. So this is u over 1, and this is theta. So this question mark, which is the hypotenuse, we square this one, we square this one, we add them up, and it's square root. And we know that sine theta is the opposite, which is u over the hypotenuse we just found. Perhaps if we put this up here, looks better. Okay. Let's look at some of the identities, refreshing everybody's memory. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So when we change the beta to minus beta, gives us this one. Cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And again, for negative, you can do that. Tan of alpha plus beta is tan alpha plus tan beta over 1 minus tan alpha tan beta. There are more identities. When we go through the process, sine to alpha becomes 2 sine alpha cosine alpha. Cosine to alpha has 3 different ways: cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. And it is extremely important to know all of them, because from time to time we use one of those. Tan to alpha is 2 tan alpha over 1 minus tan squared alpha. So sine squared alpha is 1 minus cosine to alpha over 2. If we cut this in half, we cut this one in half. Sine squared of alpha over 2 becomes 1 minus cosine alpha over 2. And it comes from here, this formula. Cosine to alpha is 1 minus 2 sine squared alpha. We've gone through that. So cosine squared alpha comes from this formula, and then you cut it in half. Alpha over 2, 1 plus cosine alpha over 2. Tan is the ratio of sine to cosine. So you can divide the sine squared alpha over cosine squared alpha, and again you can cut it in half. Alpha becomes alpha over 2, 2 alpha becomes alpha. And if you want to take the sine of alpha over 2 is plus minus the square root, the same thing for cosine and tangent. In this case, they don't need it. And as always, you look at the quadrant to make a decision as far as the positive or negative. All right, we want to use the half angle formulas to come up with the answer for sine of 195 degrees. And so 195 degrees sine, so we go with that one. So it will be sine of 390, 2 times that, divided by 2, which makes it a common arc. So 390 divided by 2. And we are going to use this formula plus minus the square root of 1 minus cosine of alpha, which means cosine of 390 divided by 2. Now, cosine of 390, remember, it's more than 360. So if you take away 360, it puts you in the first quadrant. This is the same as cosine 30. Okay. And 195 degrees, that's what we are looking for. 195 degrees. Which quadrant is that? Let me just write it. In the third quadrant, sine is negative. Sine is negative. So we use the negative value. And again, 390 is the same as 30 degrees. Subtract 360. We know cosine of 30 to be square root of 3 over 2. And if you multiply this one by 2, and this one by 2, the denominator comes out as 2, and the numerator becomes 2 minus square root of 3, still on the radical. And that's the precise and final answer. $15 is half of 30. So cosine of 30 divided by 2, obviously this is the first quadrant and it's positive. So we use this formula, and first we put plus minus, and then we know this is in the first quadrant, and all trigonometric functions are positive in the first quadrant. Cosine of 30 is square root of 3 over 2. And basically you do the same thing, you multiply by 2 over 2, and you get the same thing with the plus sign, no negative here. So multiply by 2 over 2. So this is 4, comes out as 2, and this one times this one is 2 times this one, the 2 drops. That's the final answer. Now, you can try it later on your own using cosine 15 degrees is cosine of 45 minus 30. This is another way of handling it using a cosine of 45 minus 30. Both of them are common arcs. We want to prove this identity that secant 2 theta is secant square theta over 2 minus secant square theta. And we normally start from the more complicated side, in this case, the right-hand side, which is secant squared over 2 minus secant squared. And we're going to change everything to sine and cosine. Secant is 1 over cosine. Notice we have a complex fraction. So if we look at each fraction, we notice cosine squared theta is the denominator, or in this case, the LCD, the least common denominator. Let's multiply the top and the bottom by cosine squared theta. When you multiply by the top, it just becomes 1. When you multiply by the bottom, this 2 give us 2 cosine squared theta, and this 2, the denominator goes away, minus 1. And as you recall, cosine of 2 alpha has different ways of writing. Cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. So what is this? This is cosine 2 theta. And you know the relationship between cosine and secant is that they are reciprocal. So 1 over cosine is the same as secant. So that's the proof. We want to prove this one. We start with one side. If we start with the left-hand side, where we have sine cubed plus cosine cubed over sine theta plus cosine theta, we should be able to get to the right side. And recall a cubed plus b cubed can be factored into a plus b times a squared minus ab plus b squared. So this is sine theta to the third power. This is cosine theta to the third power. So we can write this according to this as sine theta plus cosine theta, then sine squared minus sine theta cosine theta plus cosine squared. And we don't touch the denominator. Obviously, we can cross these two, and we get sine squared minus sine theta cosine theta plus cosine squared. Let's put sine squared and cosine squared next to each other. We know this is 1, and we have proved the identity. We want to solve the equation sine 3 theta is 1/2 in the interval of 0 to 2 pi. We remember that sine x equals 1/2 gives us pi over 6 and 5 pi over 6. We remember that. Now in this case, basically 3 theta is the x. And so 3 theta is either pi over 6 and we write it as pi over 6 plus 2n pi or 2k pi. Remember, this is an integer. I could write n pi or k pi. That means the same thing. And so if I divide both sides by number 3, I get theta. This, when I divide by 3, I get pi over 18. This one, I just put it over 3. Right? Now, 5 pi over 6, I'm going to add again 2n pi. Okay. And I'm going to divide by number 3. This becomes 5 pi over 18, and again, plus 2n pi over 3. Now, because this is 3 theta, we choose n to be 0, 1, 2. We don't continue. Why not? This is 3. If I choose number 3, it goes beyond the 2 pi. So let's plug in 0 here, for example. We simply get pi over 18. If we plug in 1, 2 pi over 3, because this is 18, let's multiply this one by 6. And we get 18. 2 pi times 6 is 12 pi. With the pi becomes 13 pi. We do the same thing with n equals 2, and we get those answers. Pi over 18, 13 pi over 18, 25 pi over 18. If I replace the n with 3, 3 cancels out the 3, and I get 2 pi. So pi over 18 plus 2 pi. So it's beyond that. That's why you stop at this number minus 1. We do the same thing here. If I plug in n equals 0, the answer is 5 pi over 18. If I replace the n with 1, remember, this is 18, this is 3, so I'm going to multiply this one by 6, and I'm going to multiply this one by 6. 12 pi and 5 pi is 17 pi over 18, and you can find the last one on your own. And therefore, from 0 to 2 pi, we have 1, 2, 3, 4, 5, 6 answers. If it were x, we would have 2 answers. Because it's 3 and we cut the angle into 3 pieces, then it's 3 times. We get 3 times 2, 6 answers. If it were 4 theta, we would get 4 times 2, 8 answers. All right, I'm going to solve this equation. Cosine squared minus sine squared plus sine equals 0. And we know Pythagorean identities. Sine squared plus cosine squared equals 1, because everything involves sine except this one. We're going to change this to 1 minus sine squared. So it's 1 minus 2 sine squared. And we take everything to the other side, or we can multiply both sides by negative, because I want to put this in descending order and I want this one to be positive for the sake of factoring. So you can multiply everything by negative, put it in descending order, or move it to the right, makes no difference. This is easy factoring because 2 is a prime number, and of course this is negative 1, is just 1 and negative 1. So you do the factoring, 2 sine x plus 1 times sine x minus 1 equals 0. Either this one is 0 or this one is 0. If this one is 0, sine x is negative 1/2. If this one is 0, it's positive 1. Remember, if sine x is 1/2, I want to make sure we understand how we arrive at it. If sine x was 1/2, it would give rise to the reference arc of pi over 6 or 30 degrees, right? Because it's negative, then sine is negative in second quadrant and third quadrant. In the second quadrant, we add pi. In the third quadrant, my apologies. So we say pi plus pi over 6. That's the third quadrant. And in the fourth quadrant, two pi minus pi over 6, which gives us 11 pi over 6. Sine is equal to 1 when x is pi over 2. Again, I wanted to make sure that you have no problem finding the reference arc with the positive value and figuring out which quadrant, so you can come up with 7 pi over 6 and 11 pi over 6 easily. We want to prove the identity, so we are going to use the sum cosine of alpha plus beta, because this is alpha, this is beta. So cosine alpha, cosine beta, which means on the left side, we're going to write cosine of pi over 2 cosine x minus sine alpha sine beta minus sine pi over 2 sine x. And as you know, cosine of pi over 2 is 0, sine of pi over 2 is 1. And so this goes to 0, and this is negative sine x, and that's the proof. Tan theta over secant theta is sine theta. Obviously, we start with the more complicated side, which is left-hand side. And we write tan theta as sine over cosine and secant as 1 over cosine. Clearly, if you multiply the top by cosine, the top gives you sine theta, If you multiply the bottom by cosine, the bottom gives you 1. And the answer is sine theta, and that's the proof. We want to prove this identity starting with the left-hand side. As you can see, we can use the factoring. Remember, a squared minus b squared. It's a plus b, a minus b in any order. So cosine squared plus sine squared times cosine squared minus sine squared. That's the left-hand side. We know this is 1. And we know cosine squared minus sine squared is cosine 2 theta. Tan x over 1 plus tan squared is sine x cosine x. We start with the more complicated side, which is the left-hand side. Now, 1 plus tan squared is secant squared. It's one of those Pythagorean identities. That's an identity. We're going to replace the tan with sine over cosine and secant with 1 over cosine. So the denominator becomes 1 over cosine squared. Now, if we multiply the top and the bottom by cosine squared, the top, this cosine cancels out one of them and you get sine x times cosine x. And this one cancels out this one, you get 1. So sine x times cosine x is in the numerator. The denominator is 1. So it's sine x cosine x, and that's the proof. We want to find the exact value of 2 sine pi over 8 cosine pi over 8. And we remember sine of 2 alpha is 2 sine alpha cosine alpha. And therefore, this is sine of a 2 times pi over 8 makes it pi over 4. And sine of pi over 4 is square root of 2 over 2. Two sine 45 cosine 45, the same thing. It's sine of 2 times 45 degrees, makes it 90 degrees, and sine of 90 degrees is 1. Cosine of 7 pi over 12, we can cut this into 2 pieces, 3 pi over 12 and 4 pi over 12. And 3 pi over 12 is pi over 4. 4 pi over 12 is pi over 3. Both of which are common arcs. So using cosine of alpha plus beta. So cosine alpha cosine beta, cosine of pi over 4, cosine of pi over 3, minus sine of alpha, sine of pi over 4, sine beta, sine of pi over 3. Now, cosine of pi over 4 and sine of pi over 4, both of these are square root of 2 over 2. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2, again, common arcs. In both cases, the denominator is 4. The product of these two, square root of 2, minus the product of these two, square root of 6. And we're done. Cosine of pi over 12, cosine of 5 pi over 12, plus sine of pi over 12, sine of 5 pi over 12. It's one of those formulas we've learned. And in this case, it's cosine of alpha minus beta. Take a look at this. It's the same thing. where alpha is pi over 12, beta is 5 pi over 12. So you can say pi over 12 minus 5 pi over 12. And by the way, it really makes no difference which one you write. Take a look. First of all, it becomes minus 4 pi over 12, which is this is minus pi over 3. As you know, cosine is an even function, so cosine of minus pi over 3 is the same as cosine of pi over 3, which is 1/2. Because of that, it doesn't matter that you write here pi over 12 minus 5 pi over 12 or vice versa, 5 pi over 12 over pi over 12. In the case of a cosine, makes no difference. We're going to do the same thing here. It's the sum of 60 degrees and 45 degrees that gives us 105. And therefore, we use cosine of alpha plus beta, the blue one. So cosine alpha, cosine beta, that means cosine 60, cosine 45, minus sine alpha, sine beta, minus sine 60, sine 45. And we replace the cosine 60 with 1/2, cosine 45 with square root of 3 over 2, sine 60 with square root of 3 over 2, and sine 45 with square root of 2 over 2. So these are all common arcs. Again, this is 4, this is 4, they both have the same denominator 4. This is square root of 2 when you multiply minus square root of 6. Again, the same LCD, namely 4. Sine 50 cosine 10 plus cosine 50 sine 10. This looks like sine of alpha plus beta. Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So this is sine of 50 plus 10, which is sine of 60, and that's square root of 3 over 2. Sine of 165 degrees. This is the sum of 120 and 45 degrees, both of which are common arcs. And we develop this sine alpha cosine beta, sine of 120 cosine of 45, plus cosine of 120 sine of 45. Now, 120 degrees it's quadrant 2 with the reference arc of 60 degrees. So this is the same as sine 60 because in the second quadrant, sine is positive. So it's square root of 3 over 2. Cosine of 45 is square root of 2 over 2 plus cosine of 1 over 20. Now this cosine of 120 is the same as cosine of 60, but in the second quadrant, cosine is negative. So this is minus cosine 60, which makes it minus 1/2. Okay. Sine of 45, of course, is square root of 2 over 2. So this is negative because in quadrant 2, cosine is negative. Again, 2 times 2, 4, 2 times 2, 4. So the denominator is 4. Product of these two, square root of 6, minus square root of 2 in the numerator. Precise answer, no calculators. Prove the identities. We have ln of the absolute value of secant x plus tan x plus ln of the absolute value of secant x minus tan x. We want to prove it's equal to 0. And I'm reminding you that ln of xy is ln x plus ln y. And so we're going to go this way. We're going to go to the left. That means we're going to multiply these two. I'm looking at the left-hand side. Obviously, we want to prove this is 0. So we're not going to start from 0 from the left-hand side. So we're going to multiply the two. And when you multiply, you get secant squared minus tan squared. So it's equal to ln of secant squared minus tan squared. And we remember Pythagorean identities. And if you look at this one, I hope you see that secant squared, if you move the tan squared to the right, secant squared minus tan squared becomes 1. And ln 1, you should know, is 0. Log 1 with any base is 0. Log 1 with any base is 0. This is one of those properties. Sine theta plus cosine theta quantity squared plus sine theta minus cosine theta quantity squared equals 2. Obviously, we're going to start with the left-hand side. And we are going to square that because that's the more complicated side. This gives us sine squared plus 2 sine theta cosine theta plus cosine squared plus sine squared minus 2 sine theta cosine theta plus cosine squared. So clearly, this one and this one cancel each other. We have 2 of this, 2 of that, and we know their sum is 1, and therefore the answer is 2. Two cosine theta minus square root of 3 is 0. We want to find the general solution as well as the solution from 0 to 2 pi. So cosine theta becomes square root of 3 over 2. Obviously, we can see that, right? And from 0 to 2 pi, the answer is pi over 6, as well as the fourth quadrant, 2 pi minus pi over 6, which gives us 11 pi over 6. So this is quadrant 4, 2 pi minus pi over 6. And all we have to do, add 2k pi or 2n pi to generalize it. That's all. And that means all coterminal angles, they all have the same terminal sides. We want to solve this equation, and we just do the factoring. Again, this is a prime number, 2 times 1, and this is just 1. One of them must be 1, one of them must be negative 1. It's an easy factoring. 2 cosine theta plus 1 times cosine theta minus 1 equal to 0. And again, you should always check your work for the middle term. This is cosine theta. This is minus 2 cosine theta. They add up to minus cosine theta. So either 2 cosine theta plus 1 is 0 or cosine theta minus 1 is 0. The first one gives you negative 1/2, and the second one gives you 1. So this is easy, obviously. Cosine theta is 1 when it's 0. And then 2 pi is the same as that, so 0. What about negative 1/2? First, let's discuss the 1/2 because I want to go again with the reference angle. So if cosine theta is 1/2 for just one solution, in the first quadrant is pi over 3, right? And that's your reference arc. Now, we want it to be negative, and we know cosine is negative in the second quadrant and in the third quadrant. So for the second quadrant, we write pi minus the reference arc. And for the third quadrant, I plus the reference. Okay, that's how you come up with the answer. Again, in case, whenever it becomes negative, go to the positive, find the reference arc, and it makes it easy. Find the exact value of the expression and justify. We've discussed the concept that 1 minus cosine squared is the same as sine squared, right? These two. Let's just combine them. We also know that cofunctions of complementary angles, we have seen the basic sine of pi over 2 minus alpha is cosine alpha. We've seen that. We've proved that. Same thing for cosine of pi over 2 minus alpha equals sine alpha. The rest of them follow. So sine and cosine are called cofunctions. Alpha and 90 minus alpha or pi over 2 minus alpha is called complementary. Same thing for tangent, cotangent, so on and so forth. So with that being the case, then cosine of 70 is the same as sine of 90 minus 70, which makes it sine of 20. So sine squared 20 minus cosine squared 20 equals 0. Cosine 70, cosine 20 minus sine 70, sine 20. Well, we notice this is the cosine of alpha plus beta. Cosine of alpha plus beta. So it's cosine of 70 plus 20, and we know cosine of 90 to be 0. Tan 20 plus tan 25 over 1 minus tan 20 times tan 25. We notice this is tan of alpha plus beta. Therefore, this is tan of 20 plus 25, which makes it tan of 45 degrees, and we know it to be 1. Sine of cosine inverse of 1/2 plus sine inverse of 3/5. If you call this alpha, you call this beta, you want sine of alpha plus beta. That's what we are looking for. We want sine of alpha plus beta. So if this is alpha, cosine inverse of 1/2 is alpha, then cosine alpha is 1/2. And we know it to be between 0 and pi because that's how the restriction works for the cosine inverse. In this case, a sine inverse, we call it beta. That means the sine of beta is 3/5, and it's between the negative power 2 and the power 2, the first and the fourth quadrant. So sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So we have cosine alpha. We need to find sine alpha. We have sine beta. We need to find cosine beta. So we use the identity sine squared plus cosine squared equals 1, and we say sine alpha, sine is plus minus the square root of 1 minus cosine squared, and from 0 to pi, the first and second quadrant, both of them sine is positive. So we don't write plus minus. I hope everybody can see what I'm doing here. So sine is plus minus the square root of 1 minus cosine squared. The reason we use plus because in the first and second quadrant, sine is positive. 1 minus 1/4 is 3/4, and square root of 3 remains, 4 comes out as 2. So sine is 3/5. Therefore, we are in the first quadrant, and in the first quadrant, everything positive, including cosine. And cosine Cosine, sine squared plus cosine squared is 1. Cosine is plus minus a squared of 1 minus sine squared. And we're not going to write the negative. So square root of 1 minus square this one, which becomes 9 over 25. Again, I want to make sure we understand what's going on here. So here we are saying sine is plus minus the square root of 1 minus cosine squared. The reason we use a positive because of the quadrant, and when we square 1/2, we get 1/4. And in this case, let me use a different color here. In this case, we are saying cosine beta is plus minus the square root of 1 minus sine squared. And the reason we use positive again is the first one. So 1 minus 9 over 25 is 16 over 25, comes out as 4 over 5. We are going to plug in here. So sine alpha is square root of 3 over 2. Cosine beta is 4 over 5. Plus cosine alpha is 1/2. Sine beta is 3 over 5. We get it from here. As you can see, both of them have the same denominator, 2 times 5 equals 10. This one has the numerator 4 times square root of 3 plus 3, and that's the exact answer. We leave it alone. We want to establish the identity. We start with the more complicated side, which is the left-hand side. We change everything to sine and cosine. So this becomes sine over cosine. And if we take a common denominator, it's simply the product of these two. And then this will be raised to sine theta times 1 plus sine theta plus cosine times cosine theta. So sine times 1 plus sine theta. So this one is sine times 1 plus sine theta, which makes it sine theta plus sine squared. And the product of these two is cosine squared. Now, obviously, we have 1 here. So we write sine theta plus 1. And sine theta plus 1 is the same as 1 plus sine theta. They cancel each other. And we get 1 over cosine theta, which is secant theta. In this case, obviously, we start from the left-hand side because it's more complicated. And we take a common denominator, which is the product of these two, sine theta, cosine theta. When we take a common denominator, we get sine 3 theta times cosine theta minus cosine 3 theta times sine theta in the numerator. So this is sine alpha cosine beta minus cosine beta sine alpha, and that gives us the following. Sine of alpha minus beta. So the numerator is sine of alpha minus beta, which is sine of 3 theta minus theta. The denominator, we know sine 2 alpha is 2 sine alpha cosine alpha. If we had a 2 here, this would be sine 2 theta. Because we don't, it's half of that. Okay? In essence, it's just sine alpha cosine alpha, right? So it's half of that. So we can write it in the following manner. The top is sine of 3 theta minus theta. This is half of this. So it's half of sine 2 alpha. So this one is sine of 2 theta, and this is half of that. So the numerator All right, so we have sine 2 theta over half of sine 2 theta, which makes it 2. And that's the right-hand side. We want to establish this identity. Again, the left-hand side is more complicated. We start with that. And we can change the numerator sine squared into 1 minus cosine squared. This is one way to do that. And factor it into 1 minus cosine, 1 plus cosine. Obviously, 1 minus cosine cancels out 1 minus cosine, and we apply the negative sign. We get 1 minus 1 plus cosine theta. And that's the proof. We get negative cosine theta. Just quickly, we could have taken a common denominator after we come this far. We can come up with LCD, and number 1 becomes 1 minus cosine theta over 1 minus cosine theta. And if you go that route, it's to cancel each other. So we have minus cosine theta plus cosine squared theta, or cosine squared theta minus cosine theta, which can be factored into cosine theta times cosine theta minus 1. And as you can see, when we cancel these two, because they are opposites, then when you cancel them, it gives you a sign which is a negative sign. So when you drop this, you have to put a negative sign. Which one is easier? I thought, if I expose you to both, it's not a bad idea. You choose which one is easier. We want to prove this. The left-hand side, obviously, it's more complicated. We have a couple of fractions. Sine theta plus cosine theta over sine theta, minus cosine theta minus sine theta over cosine theta. Let's take a common denominator, which is sine theta times cosine theta. Then we raise this fraction by a factor of cosine theta. We multiply this one by cosine theta. We get sine theta cosine theta plus cosine squared theta minus. We're going to multiply this one by sine theta. So minus cosine theta times sine theta, or sine theta times cosine theta, minus, and minus is plus sine squared theta. I'm assuming we have no problem doing that. So again, a quick recap: when you multiply this by this, you get this one, sine theta cosine theta plus cosine squared. When you multiply this one by this one and this one, minus sine theta cosine theta. This one has a negative sign with this one, sine theta gives you that. So I can sort of put it at top in case. I can write this one as cosine theta times sine plus cosine, and then I'm going to write minus sine theta times cosine theta minus sine theta. And so notice that sine theta cosine theta and negative sine theta cosine theta cancel each other. So we are left with sine squared and cosine squared, and sine squared and cosine squared, in any order you put them, cosine squared plus sine squared will give you 1. So we can write this as 1 over cosine times 1 over sine. 1 over cosine is secant, and 1 over sine is cosecant, and we are done. We want to establish this identity, although the right-hand side may seem to be more complicated, but we have to start with the left-hand side. It's very difficult to go from right to left. So sine of 4 theta, we know 4 is 2 times 2 theta, and we are going to use that. So assuming this is x, if it was sine 2x, or assuming it's alpha, 2 sine alpha, cosine alpha. So assume this is alpha, sine of 2 alpha. So 2 sine alpha, cosine alpha. 2 sine alpha, cosine alpha. Again, let's just put this as sort of assume this is alpha. And you see 2 sine 2 theta, cosine 2 theta. Now each one has its own formula. Sine 2 theta is 2 sine theta cosine theta. Cosine 2 theta has three different formulas. Which one are we going to use and why? When we look at the right-hand side, we see over here is all cosine. So therefore, we're going to use 1 minus 2 sine squared for that, again, because we see all sines. So 2 times, this is 2 sine theta cosine theta, and this is all sines. We're going to use 1 minus 2 sine squared. So 2 times 2 makes it 4. We are going to multiply the 4 sine theta by the parentheses. So we're going to keep the cosine, because remember, we want it to look like that. So we keep the cosine. We multiply the 4 sine theta by that. If we do that, this gives us 4 sine theta. This gives us minus 8 sine cube theta. And that's the proof.